Welcome back to the Deep Dive. Today we're tackling something that touches almost everyone's lives in some way. The medical fight against tumors.
It's a huge topic.
Yeah.
And the pace of change is just staggering.
It really is. And for this deep dive, we're going to try and give you a really clear map of how anti-cancer treatments have evolved.
And that evolution, it all comes back to one central challenge, doesn't it? The fact that cancer is, at its core, about cells that are just growing way too fast.
Exactly. So our mission today is to track that evolution across 5 major strategies. We're going from the very first broad attacks to the super precise, almost sci-fi stuff that's happening right now.
We'll look at how they work, what they're good at, and of course where they fall short.
Okay, let's unpack this.
So we have to start at the beginning, with the approach that's really defined cancer treatment for decades. Chemotherapy, our first type.
Right, chemo. It's the one everyone knows, and frankly, the one most people fear. The sources we looked at often call it the blunt instrument, or a group attack.
That's a very good way to describe it.
So what's the basic idea behind it? How does it work?
Well, the whole strategy relies on a key weakness of the tumor cell. Because cancer involves this crazy rapid growth, chemo drugs are basically poisons designed to kill any cell that's dividing quickly.
Any cell at all?
Any cell. It works by shredding the cell's DNA or just jamming up the machinery it needs to replicate. And it's effective, because cancer cells are usually the fastest dividing things in the body.
I saw one researcher describe it as watering a garden with a fire hose.
Yeah.
You're definitely going to hit the weeds, but you're also going to flatten the flowers.
That's a perfect analogy, and it points right to the biggest drawback.
Yeah.
It's completely non-selective. It has real trouble telling the difference between a cancer cell that's dividing and a healthy cell that's also dividing.
And those healthy, fast-dividing cells, that's where the side effects come from.
Precisely. That's the collateral damage. You see it in the body's fastest-growing systems. Your hair follicles, for example, which is why people lose their hair.
Right.
The cells lining your digestive tract, which leads to nausea. And maybe most critically, your blood-forming cells in the bone marrow. That's what causes anemia and suppresses the immune system.
So if it's so damaging, why is it still what our sources call an indispensable pillar of treatment? I feel like we should have moved past it.
Because for some cancers, especially ones that have spread everywhere and you can't just cut out with surgery, its broad-spectrum killing power is still the best tool we have.
So it can still control the disease.
It can control it, prolong survival. And for some specific cancers, believe it or not, it still offers the only real chance at a cure. It's a powerful weapon, but the cost is high.
That cost, that lack of selectivity, that's the huge problem. And it feels like that flaw is exactly what pushed science to develop our second type, the selective attack, targeted drugs.
Yes, this is a massive shift in thinking.
It's like going from a bomb to a sniper rifle.
That's it, exactly. The whole idea rests on finding a specific bullseye on the cancer cell that isn't on normal cells.
And what is that bullseye? What makes a tumor cell different?
Well, many tumors mutate in ways that make them express these unique little markers on their surface. You can think of them like special antennas. Normal cells either don't have them at all, or they have very, very few.
So the targeted drug is like a key made for that specific antenna's lock.
A perfect analogy. It's designed to find and lock onto only those cells with that specific marker.
So it docks with the cell.
Yeah.
And then what happens? How does that stop the cancer without the fire hose effect of chemo?
Once it binds, it messes with the signals the cancer cell needs to live. It might cut off its blood supply, or it might just tell the cell to stop dividing.
So it just shuts it down.
Or, and this is really elegant, some of the best ones actually trigger the cancer cell's own self-destruct sequence, a process called apoptosis.
Programmed cell suicide.
Exactly.
The benefit there seems so obvious. You're barely touching the healthy cells because they don't have the target.
And you just can't overstate how big of a deal this was for patients. Targeted drugs completely changed the game for so many people with late-stage cancer.
People who previously had no options.
People who had no options, or only chemo, suddenly they could achieve long-term survival. The cancer became more like a chronic disease you could manage. This was really the dawn of precision medicine.
Okay, so that jump from a chemical fire hose to a chemical sniper rifle is huge.
Yeah.
But the next step is, it's a totally different philosophy. We move away from external weapons and start trying to boost our own internal power.
Right. We're talking about immunotherapy, type 3.
Which is all about, as the sources say, waking up the immune system.
For a long time, we've known that our immune system should be the perfect cancer-fighting machine. I mean, its job is to find and destroy foreign cells. But the problem is that cancer is smart. It figures out ways to hide.
It puts on an invisibility cloak.
A very good way of putting it. So immunotherapy is all about ripping that cloak off. The strategy isn't to attack the tumor directly, but to attack the immune system itself.
How do you attack the immune system to make it better? That sounds counterintuitive.
Well, you target the brakes on the immune system. A lot of tumors put out a signal that basically tells an immune cell, hey, I'm a friend, move along. Immunotherapy drugs block that signal.
So it unmasks the tumor.
It unmasks it, and suddenly the immune cells, the T cells, can see the tumor for what it is and go on the attack.
That opens up a really exciting door.
Yeah.
If you're just fixing the immune system, does that mean this could work for many different kinds of cancer, not just one with a specific marker?
That is the incredible promise of immunotherapy. But there's always a but.
There's always a catch.
The catch is calibration. The sources are pretty clear on this. If you turn the immune system up, how do you make sure you don't turn it up too high?
You risk overactivation. The system just goes haywire.
Exactly. The same T cells that you've just supercharged to kill cancer can lose their brakes entirely and start, well, attacking everything, your own healthy tissue.
And that causes autoimmune side effects.
Severe ones. Things like inflammation in the lungs, the colon, the liver. It shows that even this amazing approach isn't a perfect drug. It has its own unique internal risks.
So if immunotherapy is like waking up the guards you already have, our next big jump feels like the ultimate personalized weapon. We're going to build a new army from scratch.
We are. This brings us to type 5, CAR-T cell therapy,
which our sources called a biological man-hunting weapon.
And it is one of the most personalized, precise things we can do in medicine today. The whole process is incredibly complex, and it actually starts outside the patient's body.
Okay, walk me through that. How do you build one of these super warrior T cells?
So first, you take blood from the patient and you filter out their T cells. Then, in a lab, you use a harmless virus to genetically engineer those cells.
You're actually rewriting their DNA.
You are. You're inserting a new gene that creates a special receptor on the cell surface. This is the CAR in CAR-PT. And this new receptor is like a super-powered targeting system, trained to find one specific marker on the patient's tumor.
So you're basically installing a cheat code onto the patient's own cells.
That's one way to think of it. And then you grow billions of these new CAR-T cells and infuse them back into the patient.
And what happens when that army gets back inside?
Two incredible things. First, they are relentless hunters. They seek out and kill any cell with that target antenna. But second, and this is the real game changer, when they find a cancer cell and kill it, they replicate.
They make more of themselves.
They expand into a massive living army inside the patient, continuing to patrol and attack for months or even years.
That's incredible, but it sounds like it still relies on finding that one perfect antenna, that one target.
It does, and that brings us back to the same limitation we saw with targeted drugs. The whole thing depends on the tumor having that antigen on its surface. If it doesn't, or if it varies, the army can get lost.
So it's not a silver bullet for everything.
Not yet. It's been revolutionary for blood cancers like leukemia and lymphoma, but it's still not 100% effective, and it can have some very serious side effects of its own.
Okay, so that target dependency is a recurring theme. Which brings us to a really fascinating technology that kind of bridges two of these ideas. It's our type 4 ADC drugs.
Antibody-Drug conjugates.
Yeah, and the sources call these biochemical missiles. I love that description.
It's incredibly accurate.
Yeah.
Because that's literally what they are. They're built in two parts, a navigation system and a highly toxic warhead.
Okay, break that down for me. What's the navigation system?
The navigation system is an antibody, that's the A in ADC. It's engineered to do one thing, find and lock onto a specific marker on a cancer cell, just like a targeted drug.
And the warhead.
The warhead is a molecule of an extremely powerful chemotherapy drug. We're talking something that's way too toxic to just inject into someone's bloodstream by itself.
Right. And here's where it gets really interesting. How does the missile make sure the warhead only goes off in the right place?
That's the magic of the C, the conjugate, the linker. The missile travels through the bloodstream fully armed, but the warhead is safely attached. It's only when the antibody finds a tumor cell and binds to it, and the whole missile is pulled inside the cancer cell.
That's when it explodes.
That's when enzymes inside the cell cut the linker and release the warhead. So you get this massive, concentrated burst of poison, but only inside the target cell.
So you're maximizing the kill power right where you need it and minimizing the damage everywhere else.
That's the goal, a much wider therapeutic window. It's more effective than a targeted drug and way less toxic than traditional chemo.
So where are we with these missiles now? Are they in use?
Oh yes. ADCs are one of the hottest areas in cancer research. It's still hard to get the precision absolutely perfect, so there can be side effects if some of the drug detaches early. But there are already several on the market, with dozens more in trials. This is a field that is going to deliver some big surprises.
So when you pull all of this together, what does it mean for you, the listener? We've just mapped this incredible journey.
We really have, from the widespread killing of chemo to the precise striking of targeted drugs.
And these new biochemical missiles.
And then to actually activating and engineering the body's own cells with immunotherapy and cell RRT.
The big takeaway here seems to be a constant, relentless drive toward more efficiency and less damage.
Exactly. For decades, the best cancer treatment was just the most powerful poison you could survive. Now, the best treatment is the smartest one, the most precise one.
And the future seems to be in combining them, right? Using one to set up the other.
Absolutely. The complexity is just going to keep increasing. And if you connect all these different technologies, from brute force to bioengineering, it tells you something really fundamental about where we're headed.
Which is?
That this is no longer one single battle. It's a whole series of specialized, intelligent, and evolving fights.
Which leaves us with a pretty big final thought for you to chew on. As medicine creates these incredibly precise, personalized, and often very expensive treatments like CAR-T and ADCs, how do we make sure that everyone who needs them can actually get them?
We may be solving the scientific challenges, but the challenge of access and equity on a global scale, that's really just beginning.
Something to think about. Thank you for diving into the sources with us today on The Deep Dive.